In Module 2, we will consider multiple regression models that include interaction terms for the predictors, as well as categorical predictors. So let's start with the assignment prep and see how we can use interaction terms in a model and how we can use categorical predictors in addition to the quantitative predictors that we worked with in the previous week. So here is module 2 assignment prep, and in this assignment we will be working with the car dataset. This is the same dataset that you used previously to create multiple regression models. So let's start with step 1. Please make sure to go over these guidelines here and the information on the dataset. These are the variables and what these variables represent. And just like before, you'll notice that we have variables that are quantitative, and then there are some variables that are qualitative. And in the first step, the code block that is included here loads the dataset from the CSV file, converts the appropriate variables to factors. So these are the categorical variables that need to be converted to factor variables. And then it prints just the first 6 rows of the data. So let's run this code block and see what we get. So here's the data set. This is the first 6 rows, and we will be working with some of these variables in the next steps. In step 2, we will be subsetting the data and creating the correlation matrix, just like we did during the last week for the variables that we will be working with. And these variables include miles per gallon, again, that will be the response variable, and the predictor's weight and rear axle ratio. So let's run this code block and see what we get. So here is the subset data. This shows the first 6 rows of the data set. And as we can see, we only have 3 variables. And then it also prints the correlation matrix for miles per gallon, weight, and rear axle ratio. And clearly we can see that the correlation coefficient for weight and miles per gallon is negative 0.8677. I would say that that is a significantly negative correlation. And then the rear axle ratio and miles per gallon is 0.6812. That's also somewhat um, moderate to strong positive correlation. Step 3 involves a multiple regression model that uses an interaction term. Let's go through this information to see why an interaction term is relevant for this model. So in this step, you will create a multiple regression model for fuel economy as the response variable and weight and rear axle ratio as predictors. So last week, you created a multiple regression model where the response variable was modeled using several predictors. And up until this point here, it's a fairly simple model. You just have 2 predictors and you're using them to model the response variable. Now let's see what else is given here. It says a numerically higher rear axle ratio, that's one of the predictors, sends more of engine's available torque to the tires. However, this reduces the fuel economy. We expect that fuel economy and weight of the car are negatively correlated. That's what we saw in step 2, meaning that as weight decreases, fuel economy increases. However, the rate of increase in fuel economy will be driven upward by a numerically lower rear axle ratio. And this is why a multiple regression model in which the 2 predictors interact should be considered here. So the general form of this model is given here. Expected value of y, that is the response variable, equals beta naught, the y-intercept, plus beta 1 x1 plus beta 2 x2. Up until this point, this is the same, pretty much the same multiple regression model that you worked with previously. But now we have this additional term here, plus beta 3 x1 x2. And the way you can tell that this is an interaction term is because you see here that x1 and x2 predictors are being multiplied in a way. And that is how you know that there is interaction between the two variables. So again, y is the fuel economy, x1 is the weight, and x2 is the rear axle ratio. And if you look at this code block, you'll see that again, we're using the LM function that we used previously. We have the miles per gallon tilde weight plus drat. Drat is the variable name for rear axle ratio. And this is how we're going to code interaction between the two variables. So you write the first variable. For example, here the first predictor is the weight. So you write the variable name for weight, and then you put a colon sign that is an indication of interaction, and then the variable name for the second predictor, which is drat. Now, in general, multiple regression model, there are models where not all of the variables will interact with each other. There will be predictors that will not interact. And so this is really something that statisticians and analysts have to think of before creating a model, whether it makes sense to include interactions, and if yes, then which interactions should be considered. For example, I could have had an extra variable here, another predictor, x3, that may not interact with x1 and x2. So the model then would have just included one additional term for x3, and there would only be one interaction of x1 and x2. So to summarize, this is something that you will have to think about for the model that you're creating in future. In at least in this course, you will be provided guidance on whether the interaction is necessary or not. But when you go in the in the real world and you're creating these models, you may have to consider whether an interaction is needed or not. So let's just run this model and see what the output is. So here's the output, and you will notice that the output looks almost exactly the same as last week. You get your estimates for the betas, that's given here. So the estimate for weight is 3.884, for rear axle ratio is 8.494. And notice now you also have the estimate for the interaction term, that is negative 2.543. And that is pretty much it. Once you know your estimates, you can replace the betas here with these estimates and create your multiple regression model. The statistics that are printed are the same as you studied last week. You have the r squared, the multiple r squared given here. So what this means is that 79.96% of the variation in the response variable is explained by the model that uses these predictors and the interaction term. You can see that the adjusted R square is 0.7782. The overall F test is or has the F statistic as 37.25 with a p-value of almost zero. And so the model is significant. And now if you look at the individual predictors, you can see that at least two of these terms are significant, rear axle ratio and the interaction term. And scrolling down, Once you have your estimates, you can write them. Um, you can replace the betas in the general equation with these estimates, and then come up with this multiple regression model. So this is the model here, and now the challenge here is is to understand how we can interpret the beta estimates. So recall last week, if we only had this model up until here and we did not have the interaction term, then we could say that a unit increase in predictor x1 would cause an increase in the response variable by a unit 3.8840. Similarly, 1 unit increase in predictor x2 would lead to an increase of 8.4940 units. That's what we discussed last week. And I'm talking in terms of units here. Please make sure when you interpret the beta estimates that you use um, the appropriate terms here. For example, weight would be measured in pounds. Fuel economy is measured in miles per gallon, and so on. So that's how we interpreted the beta estimates last week. Well, we now have an interaction term, and because of this interaction term, you see here that it includes variables x1 and x2 both. We cannot use the same strategy to interpret the beta estimates. So the beta, for example, in the case of x1, it is incorrect to say that a unit increase in x1 causes an increase in response variable by 3.8840 units. We have to consider the interaction term. So let's now discuss how to properly do this interpretation. So let's focus on interpreting the estimated coefficient of rear axle ratio variable when the multiple regression model includes an interaction term that has this term in it. And the same thought process can be used to interpret the beta estimate for the weight variable. But let's start with the rear axle ratio. So the first bullet here says, let's assume that there was no interaction present, and therefore the multiple regression model would just be 5.55 plus 3.884 x1 plus 8.494 x2, and that's it. And so if that was the case, then the fuel economy of the car would increase on average by 8.494 for each unit increase in rear axle ratio. So if x2 went up by 1, then the fuel economy would increase by 8.494. That's how you interpreted this coefficient last week. However, now weight and rear axle ratio interact in the model, so there's an interaction term, and therefore we need to be careful about interpreting the coefficient. So the rate of change of average fuel economy with rear axle ratio now depends on the value of the weight of the car. And the reason is that you have this interaction term here. So this value of the weight of the car, x1, will change the the coefficient of rear axle ratio, and hence it would change how you interpret it. And how would that happen? Let's see. The estimated coefficient for x2 can be written as follows. So notice that if you just look at this part of the multiple regression equation, you notice that x2 is a common factor here. So if I take this common factor out, I can rewrite this part of the equation as parentheses 8.4940 minus 2.5430 x1, and then parentheses closed, x2. x2 is the common factor, so I took that out and I rewrote this part of the multiple regression model as follows. Now notice here that this in itself is a coefficient. It's an estimated coefficient for x2. The only difference here is that in this estimated coefficient, x1 is a variable. It can take different values, but that's what we mean. The different values of weight of the car would give you different estimated coefficients for x2. So for example, and so therefore, the estimated coefficient for x2 is now 8.494 minus 2.543 x1. Now, suppose we have a car with weight 3.440. So this is just an example. So let's say we have a car that has a weight of 3.440. The estimated coefficient for rear axle ratio based on this equation here can now be calculated as all you do is plug in 3.440 here in x1. So that's what I'm doing here. Once you plug it in and you solve, you get 5.591. And that would be the estimated coefficient for x2, 5.591. So in other words, we estimate that the fuel economy of a car with weight 3.440 will increase by 5.591 units for each unit increase in rear axle ratio. Now, clearly this is different than 8.494 from the first bullet, where we assume that there is no interaction. Because there is an interaction now, so the estimated coefficient is different and therefore the interpretation is different. Here's another example. Now that we have a car with weight 2.32, again, we plug that into this equation here, 2.32, and once you do that, you'll notice that we will get 2.59. So now the average fuel economy is increasing by 2.59 units for each unit increase in the rear axle ratio. So clearly you can see here that the different values of weight of cars are giving you different estimated coefficients for x2, and therefore the interpretation for average change in the response variable is different. So please be sure to do this interpretation correctly. Make sure you go over this in detail, go over this more than once so that it makes sense. And whenever you have an interaction term present, you have to be very careful with interpreting the estimate appropriately. So the last bullet is simply just that the rate of increase in fuel economy now varies due to presence of the interaction term. So we can use the same strategy to interpret the estimated coefficient for variable weight. And what I would do there then is to first look at the term that includes the weight variable, that is 3.884x1, and then include the interaction term that includes weight, which is negative 2.543x1, x2. So I've typed them here, and notice that x1 is the common factor, so I will take that out, and the rest of this will be the coefficient, the estimated coefficient for x1, that is the variable weight. Now suppose x2 takes a value of 2. So I would plug in 2 here. I would solve and get negative 1.202 x1. And so now this is the estimated coefficient for the weight variable. And the interpretation here would be that the average fuel efficiency would decrease by 1.202 units for a unit increase in the weight variable. By the way, do recall that weight has been quoted in terms of thousands of pounds, and so a unit increase means a 1,000 pound increase. So that is the appropriate interpretation. So I think the challenge usually here is that um, it is critical to come up with the correct terms when interpreting a predictor. So, for example, when we considered weight, uh, when we wanted to interpret the coefficient for weight, we took the term that includes the weight variable here and the interaction that includes weight. And then we worked using those two terms to come up with the estimated coefficient. And likewise, when we considered rear axle ratio, we took the term that includes rear axle ratio, that's 8.494x2, and the interaction that includes the same term, and worked with those two terms to come up with the coefficient, the estimated coefficient. And this is really the challenge here. And once you have set that up, it's a fairly simple calculation, and then that would that would then lead you to properly interpreting the estimated coefficient. Section 4.8 in Zybook covers interaction terms. So I highly recommend that you read this section. It includes excellent examples. It also includes visuals for various estimated coefficients when interaction terms are included. So, and I think that these visuals also help to solidify understanding of how the interpretation uh, is very unique when interaction terms are present. Next, we will consider qualitative predictor. So up until now, we've only worked with quantitative predictors that take numeric values. We have not considered qualitative predictors that are factors. So for example, in this data set, the transmission variable AM is a qualitative variable with two levels, manual and automatic transmissions. So clearly these are not numeric variables. They are kind of like identifiers that identify a manual transmission and automatic transmission. So how can we use qualitative predictors in our regression model? And for this part, I think it's a good idea to first go into Zybook, section 4.9, and understand the process of using qualitative predictor in a multiple regression model. Section 4.9 in Zybook covers categorical predictor of variables. These are variables that have qualitative values, and our task is to somehow use them in multiple regression models. So there's a really nice data set in this section for weight data for humans and dolphins. So you'll notice that this has weight in pounds. So clearly that is a numeric variable, takes numeric values here. But then there's a variable species that takes levels human and dolphin. And we would like to use this as a predictor in a multiple regression model. And the process of using this in a regression model starts off with thinking of a variable called dummy indicator variable that will be used to specify a category of a categorical predictor. So for example, let's consider this species human and dolphin as an example. So clearly this variable has two levels, human and dolphin. So we can come up with a dummy variable, and let's call this x1. And this variable will take a value of 1 if it's a human, or it will take a value of 0 if species is not human. Okay, so this is what we call a dummy variable. When we have just two levels of a categorical variable like species, we just need one dummy variable to code it. Either a species is human or it's not human, and in this data set, not human essentially just means it's a dolphin. So suppose that species took values human, dolphin, and shark. So now we have three levels. So how can we code three levels using dummy variables? How about we use two dummy variables? So we will have dummy variables x1 and x2. We can code x1 similar to how we did before. X1 equals 1 if species is human, or 0 if species is not human. Now, it's important to realize here that not human in this case means it could be a dolphin or a shark. In the previous example, when we just had two levels, not human just meant dolphin, and that was enough to represent all of the levels of categorical variable. This time it's not enough, so we need that second variable. So I can code the second variable as x2 equals 1 if dolphin, or it's 0 if not dolphin. So now we have covered all different levels here. If a species that we have in the data set is human, then x1 would take a value of 1 and x2 would take a value of 0. If that species is dolphin, then x1 would be 0 and x2 would be 1. If the species is shark, x1 would be 0 and x2 would be 0. So that two dummy variables here are enough to represent three levels of the categorical predictor species. Similarly, if we consider the general case, so suppose we have a categorical variable that takes n levels, okay? Then we would need n minus 1 dummy variables in the regression model to represent them. So in step 4, we are considering a multiple regression model that uses transmission variable, AM, that is a categorical variable. And this variable takes two levels, manual transmission and automatic transmission. So because it takes two levels, we just need one dummy variable in the multiple regression model to represent it. And so that's what's given here. So let's first consider the general form of the regression model. This model uses weight and rear axle ratio as predictors, as well as their intersection, just like the previous step. But now it has this extra x3 variable that is the dummy variable for transmission. And again, recall because there are only two levels for transmission, we just need one dummy variable to represent it. So this would be the general form of the regression model. Now, the nice thing is that once you use the regression model in R using the LM function to create the model, R will automatically generate the dummy variables for you. So you don't have to tell R how many dummy variable it needs to create. Just as long as you have coded the variable in this step as a factor, once you've created the factors for it, R knows how many dummy variables it needs to create. So in this case, for example, take a look at this. I have miles per gallon being modeled using weight, rear axle ratio. They're interaction as well as the AM variable um, as a predictor. And so R knows that this is a factor and it has two factors. And so it's going to create one dummy variable for you. So let's run this step and see what we get. So here it is. And now you will notice that you have not you don't only have the estimate for weight, rear axle ratio, and the interaction between those two. You also have here AM1, and it has an estimate of negative 1.464. And AM1, if you scroll up, AM here is given in this table. It's the transmission, and 1 means is manual. Okay, so this dummy variable given here is using manual as AM equals 1 and not manual as AM equals 0. So that's what this is. And then once you know this, you can easily create your regression model by substituting these estimates for the betas here. Okay, so just like how you create the regression models or how you have done this before, it's very simple to just take these estimates, plug them in here to create your regression model. And so now you can see that using qualitative predictors is actually quite simple in R. It's just that you have to have intuition for why R is printing these qualitative predictors here as dummy variables. So if for example, the transmission variable had 3 levels, so there was one extra level here, you would have two dummy variables and you would see two dummy variable outputs here with their respective estimates. So just please make sure that you are aware of that and that you use uh, the model appropriately. Always start off with the general form first so that you know what to expect in the output. And then once you get the output, take the estimates, plug them in, and that's your regression model. And then just like before, you get all of your statistics that are important to analyze, and um, you get your overall F statistic, and it also tells you which estimates are statistically significant. Now we move on to step 5 to get the fitted values. We're going to use this model here. And this is just like the previous week. Fitted values are predicted values. So let's click on this. So here are the predictions for fuel economy uh, the, using the data, using the data set, and um, in other words, using the predictor values from the data set and using the model to predict the fuel economy. So these are all your predictions. And then the next step is your residuals. That's the difference between the actual fuel economy given in the data set and the predicted fuel economy using the regression model we just created. These are all your residuals. And then you have the diagnostic plots. Remember we studied this last week. Clearly this seems like um, a random split, and so looks good. We go to the next step, the QQ plot for residuals. The residuals do show significant deviation from normality. So this could be an issue with the model. And we go create our confidence intervals in step 9. These are for the parameter estimates, um, the estimated coefficients for your predictors. So this is the 90% confidence interval. And then you have your prediction and prediction intervals as well as the confidence intervals. So we're using this. Remember to always read the guidelines here. We're using the case where the weight is 3.88, rear axle ratio is 3.05, and the transmission is 1, which is the coded variable for an automatic transmission. So once we use these values, we can now get our prediction interval and the confidence interval for the prediction. So we here's what we get. Once you use these values in the model, you will get a prediction, a predicted fuel economy of 15.0672. That's your prediction. It's the same, okay, in both the cases of confidence interval and the prediction interval. The predicted value will just be one value that is predicted by the model once you plug in these predictors. Um, but then the prediction interval again is wider than the confidence interval, just like I mentioned last week, because in prediction interval, you're really predicting just one specific value. And so there's more uncertainty in predicting just one value. Whereas the confidence interval is kind of like it considers average prediction. And when you have an average prediction, what you really have is the case where you're saying that if I were to collect a sample um, of several cars that have these features, then the average prediction would be 15.0672, and the confidence interval is for that average. So it's um, so there's less uncertainty because now you've considered sort of like a sample, and so therefore the interval is narrower. Okay, so that's your prediction and confidence interval, and that's pretty much it. After this, you essentially have to use um, problem set 2, the homework assignment for this week, to create your model that will utilize interaction terms as well as categorical predictors that use dummy variables.